Hello friends, welcome back to my YouTube channel. Welcome to my discussion on liquid extraction. This is part number 10 of the discussion, and in this I will be continuing my discussion on stage-wise liquid extraction. And today I will talk about multi-stage cross-current liquid extraction. So at the end of this discussion, you'll know everything about multi-stage cross-current liquid extraction. So let us begin discussion. To begin with, let us just briefly understand a stage-wise contact, because stage-wise liquid extraction, it is carried out in stage-wise contact equipment. So in this stage-wise contact equipment, there are stages, and for liquid extraction, in each stage there should be a provision to intimately mix the feed solution with the solvent, and after the resulting mixture settles into raffinate and extract phases, there should be a provision for physically separating the extract and raffinate phases. So this kind of arrangements is possible if in each stage you have a mixer and a settler. That is, it is possible if each stage is constituted of a mixer and a settler. You can represent that schematical. So you have a mixer followed by a settler, and this combination forms one stage. So feed containing A and C. A is the carrier solvent and C is the solute to be recovered. It is contacted with the solvent. In our notation, in our discussion, we have denoted solvent by B. So these two liquid phases, they will be intimately mixed in the mixer. The resulting mixture will be transferred to the settler, where it will settle in two layers, the extract layer and raffinate layer. So after the mixture settles into extract and raffinate phases, the two phases are physically separate. So there is provision of mixing, and there is also provision for physical separation of raffinate and expectorants. So this combination, it forms one stage in this case. As per requirement, you can arrange multiple stages. Multiple stages, they can be arranged in desired cascades. What is a cascade? Cascade of multiple stages. It is nothing but an arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. So for example, if you consider a cascade of two stages, let us say this is stage number 1 and this is stage number 2. Then if these two stages are arranged in such a way that the output of stage number 1 is input to stage number 2, so then we say that there is a cascade of two stages. So that's why we are saying a cascade of multiple stages. It is nothing but an arrangement where multiple stages are arranged so that an output from one stage is an input to the next stage. And two such cascades are very common in liquid extraction. So one is cross current cascade and the other one is counter current cascade. Today we are going to talk about cross current cascade. In my future videos, I'll be talking about counter current cascade. Today, let us know more about counter current cascade. So liquid extraction in cross current cascade, we call it as multi-stage cross current liquid extraction. Multi-stage cross current liquid extraction. How this is carried out? The raffinate phase is successively contacted with fresh solvent in multiple stages. So I'll shortly show you the schematic diagram, but let me tell you in brief over here. So if you have two stages a cascade, a cross current cascade of two stages, stage 1, stage 2, and the feed solution is contacted with the solvent. So out of stage number 1, the raffinate phase will be coming out and the extract phase will also come out. The raffinate phase is sent to the next stage where it is contacted with fresh solvent, so that you get an extract phase out of stage number 2 and the final raffinate phase. So this is how multi-stage cross current liquid extraction is carried out. We will know more about this particular operation. So the point is, raffinate phase is successively contacted with fresh solvent in multiple stages. And this operation you can carry out it in a batch-wise manner or you can carry out in a continuous manner. Okay, now let us look at a 3-stage cross-current liquid extraction operation. So the system that we are going to consider in our discussion, the ternary system involved, has 3 components in it, A, B and C. C is the solute, which is soluble in both A and B. A and B, they are soluble in each other, but they are soluble only to a limited extent, which is a common case in liquid extraction. C soluble in A and B partially soluble in each other. The feed solution in this case is A plus C, where C is the solute to be recovered. The solvent is B. If you are using pure solvent, then it will be just B. And if you are using a reused solvent, it will contain all the 3 components, that is B, C and A, where A and C, they will be present in little amounts. So if you are using a recovered solvent, then all the 3 components will be present. A and C, they will be present in minor quantities or minor amount. The feed solution and the solvent, they are contacted with each other in a 3-stage cross current liquid extraction operation, 3-stage cross current operation, and you can carry out this operation either batch wise or in a continuous manner. Okay, now let us look at the schematic diagram. So let the circles represent stages. So this is stage number 1, stage number 2 and stage number 3. Feed is admitted into stage number 1. So feed F is its mass if the operation is batch wise, or the mass flow rate, that is mass per unit time, if the operation is continuous. And XF is the weight fraction of solute in the feed. It is contacted with the solvent phase. S10, it represents mass or mass flow rate for the solvent phase. Mass if it is a batch wise operation, mass flow rate if it is a continuous operation. So S10 indicates the solvent that is entering stage number 1. S10 is its mass of the solvent admitted to stage number 1. And if the operation is continuous, it is mass flow rate of the solvent phase that is admitted to stage number 1. And then YS is weight fraction of the solute in the solvent phase that is admitted to stage number 1. Then we get raffinate out of after extraction is completed in stage number 1. We get the raffinate phase. R1 is the mass or mass flow rate of that raffinate phase, and X1 is weight fraction of the solute in that raffinate phase. Then we also get the extract phase. E1 is either mass if it is batch operation or mass flow rate if it is a continuous operation, and Y1 is weight fraction of the solute in the extract that is coming out of stage number 1. Then the raffinate phase that comes out of stage number 1 it is sent to stage number 2, where it is contacted with fresh solvent. It is contacted with fresh solvent. So here S20, it represents mass or mass flow rate of the solvent that is going to stage number 2. And YS is the wet fraction of solute C in it. Then we will be getting raffinate phase out of stage number 2. Let R2 represent mass for batch-wise operation or mass flow rate for continuous operation. X2 is wet fraction of C in the raffinate phase. Then likewise you have extract phase, which has E2 as mass or mass flow rate depending on whether it is batch-wise operation or continuous operation. Y2 is the wet fraction of solute in it, wet fraction of solute C in it. And finally, the raffinate phase then is admitted into stage number 3, which is contacted with fresh batch of solvent. S30 will be its mass or mass flow rate. YS will be the wet fraction of solute in it. Then you'll be getting final raffinate phase coming out of stage number 3. R3 will be its mass or mass flow rate, and X3 will be the wet fraction of solute in it. And for the extract phase that is coming out of stage number 3, E3 will be its mass or mass flow rate, and Y3 will be the wet fraction of solute in it. So you can just understand in each stage the raffinate phase is successively contacted with fresh solvent. So this is cross current liquid extraction. In this case, we have considered a 3-stage cross current liquid extraction where the raffinate phase is contacted with fresh solvent 3 times. Each time in a new stage. So stage number 1, stage number 2 and stage number 3. And then you can get composite extract phase by adding all the extract phases that you get from each stage. So you can get a composite extract phase which is addition of E1, E2 and E3. So that is mass of composite extract, or you can say mass flow rate of composite extract if it is a continuous operation. So I hope you have understood the schematic diagram. If you have any doubts, you please mention them in the comment section. Okay, let us. Now we will do analysis for each stage, or we will understand calculations for each stage. Let us start with stage number 1. Let us look at stage 1 calculations. So for our understanding, let us take stage number 1 into the discussion. So stage number 1, where feed is contacted with the solvent and you get raffinate out of it and extract out of it. So before you start your calculations for stage number 1, these things are known to you. F, that is mass or mass flow rate of the feed, is known to you. XF, that is wet fraction of solute in it, is known to you. S10, that is mass or mass flow rate of the solvent phase to stage number 1. This is also known to you. And wet fraction of solute in the solvent phase, that is YS. This is also known to you. So these 4 you can say parameters, they are known to us for doing calculations for stage number 1. Now let us look at the calculations. Let us first look at steady state total material balance. Steady state total material balance means material balance that is taken at under steady state conditions. Input is equal to output. So it will be input is F plus S10, the input. When these 2 phases, they are mixed in the first stage, initially a mixture will be formed. Let M1 represents its mass or mass flow rate for the mixture, and then when this mixture is allowed to settle, it will settle into 2 layers, raffinate and extract layers, and then they will be physically separated from each other. So F mass of feed plus mass of solvent is equal to mass of the resulting mixture, which then separates into raffinate and extract layer. Therefore, this will be equal to mass of extract layer plus mass of raffinate layer. So M1 represents mass or mass flow rate of the resulting mixture when feed and solvent are mixed in stage number 1. E1 represents mass or mass flow rate of the extract phase obtained from stage number 1. R1 represents mass or mass flow rate of the raffinate phase that comes out of stage number 1. So mass if the operation is batch wise and mass flow rate if the operation is continuous. You please remember this. Then let us write steady state material balance for the solute, that is for C. So it will be F into XF, that is total mass into weight fraction. So F into XF plus S10 into YS, that is equal to M1 into XM1, where XM1 is the weight fraction of C in the mixture, is equal to E1 into Y1 plus R1 into X1, and let us call this as equation number 2. So from equation number 2, we get M1 into XM1 is equal to F into XF plus S10 into YS. That is XM1 will be equal to F into XF plus S10 into YS divided by M1. So everything on the right hand side of this equation is known to us. So you can simply use the known values and get the value of XM1. So with equation 1, you can get XM1 as F into XF plus S10 into YS divided by F plus S10, because according to equation number 1, M1 is equal to F plus S10. Okay. So what we have then for stage number 2, we have considered stage number 1 separately, and for this stage we have written the steady state total material balance, and then we have written steady state material balance for the solute C. And now let us follow this material balances on the ternary diagram. So in my discussion, I'll be using this the ternary diagram on rectangular coordinates. Their nx and ny, they are plotted on the x-axis, and x and y, they are plotted on the y-axis. In this case, nx is weight fraction of B in the raffinate phase, and ny is the weight fraction of B in the extract phase when they are in equilibrium with each other. Then x is weight fraction of C in the raffinate phase, and y is weight fraction of C in the extract phase. So if when you plot nx against x, that is weight fraction of B in the raffinate phase against weight fraction of C in the raffinate phase, you get one part of the binodal solubility curve. And when you plot ny against y, that is weight fractions in the extract phase, you get the other part of the binodal solubility curve. So you get the binodal solubility curve. Now we are going to follow the material balance equations written for stage number 1 on this diagram. So this what I have shown over here, these are given tie lines, the given equilibrium data, and these tie lines are connecting equilibrium concentrations that are in equilibrium with each other. So for the sake of understanding, I have shown the given tie lines. The given tie lines I have shown on the ternary diagram. Now for stage number 1, we have to start with by locating point F. So point F is located at 0 xf. The coordinates of point F are 0 and xf. That is, it will be located on the y-axis where y is equal to xf. So this is a point where y is equal to xf, and that will be the point F. Then we have to locate point S. Point S, it is located at with this coordinates nys and ys. What is nys? Nys is weight fraction of the in the solvent phase, and ys is, weight fraction of C in the solvent phase. Okay. So I'll just locate Ys over here, and then I will locate NYS over here. I'll get this point. This point is nothing but point S that represents the solvent phase. And if you are using pure solvent, then Ys will be 0. That is, there will be no solute in it, and there will be only B in it, pure B. So in that case, NYS will be equal to 1. So in that case, S will be located where S will be located at 1 on the x-axis, where NYS is equal to Y. So for pure solvent, where Ys is 0 and NYS is equal to 1, because in that case, there will be no A in it, there will be no C in it, there will be only B in it. That's why NYS is equal to 1. So therefore, S is located at 1, 0. That is, it is located on the x-axis. So after point F and S are located, next task is to connect F and S. So F and S will be connected by a straight line. Okay, now next we have to locate point M1. For locating point M1, the coordinates required are NM1 and XM1. So out of this, even if XM1 is known to us, we can locate point M1. So before that, what is here? NM1? NM1 is weight fraction of B in the mixture. Okay, but we are going to use XM1 to locate M1. So on the y-axis, locate XM1. Then go to the line FS, line connecting points F and S. So that will give the intersection point with the line FS. I am calling it as M1. This M1 represents the mixture that is obtained in stage number 1. So mixture M1 then settles into raffinate. When it is allowed to settle, it settles into raffinate and extract phases, which then after some time will come to equilibrium. Therefore, the meaning is this point, it lies on Fs, at the same time it lies on a tie line. So the tie line, the constant tie line I have shown over here with the red color. The end point of this tie line, they represent raffinate and extract phases, like points R1 and R1. So point R1 represents the raffinate phase that is obtained out of stage number 1, and E1 represents the extract phase that is obtained out of stage number Y. You please remember, on this diagram, R1 and E1, these are points that are representing raffinate and extract phases respectively. And when you use them in material balance equations, over there they are representing quantities of raffinate and extract. So let us. So the y coordinate of point E1 is y1. So if you just read the y coordinate of this point E1, that is from E1, if you travel horizontally to the y-axis, the value that you will be getting is y1, and the y coordinate of this point R1, will give us x1. It will give us x1. So at the end, that means for stage 1, at the end of our calculations for stage number 1, we know these values x1 and y1, and then we are going to use these values to find out the quantities of raffinate and extract phases that are obtained from stage number 1. So equation 1 is F plus S10 is equal to M1, that is equal to E1 plus R1. So from this I can write E1 plus R1 is equal to M1. Let me call this as equation number 3. Then equation number 2, it was Fxa plus S10 into Ys, that is equal to M1 into Xm1, that is equal to E1 into Y1 plus R1 into X1. So I can write it like E1 into Y1 plus R1 into X1, that is equal to M1 into Xm1, and I am calling it as equation number 4. In equation number 3, And equation number 4, there will be two unknowns, E1 and R1. E1, the quantity of raffinate, and R1, the quantity, E1 the quantity of extract, and R1, the quantity of raffinate. So you have two equations, you have two unknowns. You can solve those two equations simultaneously and get the values of R1, quantity of raffinate out of stage number 1, and quantity of extract, that is E1, out of stage number 1. So at the end of calculations for stage number 1, you know Y1, you know X1. You are using these two values to get equation 3, equation 4, and then you are solving equation 3 and 4 to get the quantities of raffinate from stage 1, that is R1, and quantity of extract from stage 1, and the quantity in this case, it is represented by E1. Okay, so I hope the calculations for stage number 1, they are clear to you. Okay, now let us understand calculations for stage number 2. So first let me show you the stage. Input to stage number 2 is the raffinate phase that is coming out of stage number 1. It is contacted with a fresh solvent phase, whereas S20 is its mass or mass flow rate, depending on whether it is batch wise or continuous operation. Ys is the weight fraction of solute in it. So at the end of operation, at the end of extraction in stage number 2, you get a raffinate phase with R2 as its mass or mass flow rate, X2 as weight fraction of solute C in it. You get extract with E2 as its mass or mass flow rate, and Y2 as the weight fraction of solute C in it. So again we are going to write. So before we start calculating calculations for stage number 2, these quantities are known to us. R1 is known from calculations for stage number 1. X1 is known from calculations for stage number 1. S20 is known to us. Ys is also known to us. So with this 4 quantities known, we are going to write steady state total material balance for stage number 2. So it will be written as R1 plus S20. Raffinate is mixed with solvent. So R1 plus S20, it will form a mixture with a mixture whose mass or mass flow rate is M2, and then it will separate into raffinate and extract phases. Therefore, the steady state total material balance is R1 plus S20 is equal to M2, that is equal to E2 plus R2. I am calling this as equation number 5. Then I will write steady state material balance for solute C, and you can easily follow that. R1 into X1 plus S20 into Ys, that is equal to M2 into XM2, that is equal to E2 into Y2 plus R2 into X2, and I am calling this as equation number 6. From equation number from equation 6, I can write M2 into XM2, that is equal to R1 into X1 plus S2 into Ys, that is XM2 is equal to R1 into X1 plus S20 into Ys divided by U2, that is, and from equation number 5, I can write equation for M2. So ultimately I'll get XM2 as R1 into X1 plus S20 into Ys divided by R1 plus S20. So in this equation on the right hand side, each term is known to us. The value of each term is known to us. So you can use those values to get the value of XM2. Okay. So we have written steady state total material balance for stage number 2. We have written steady state material balance for solutes C in stage number 2. Now let us follow this material balances on the ternary equilibrium. So at the end of calculations for stage number 1, we had got this diagram. Now we are going to continue with this. For stage number 2, first thing that you have to do is you have to connect R1 with S, because you are contacting raffinate from stage number 1 with fresh solvent, and this activity, it is followed on the ternary equilibrium diagram by connecting R1 points R1 and S on the diagram. So R1 is connected with S. So I get this straight line. Then I have to locate point M2. For locating point M2, I need its coordinates. Its coordinates are N, M2 and XM2. But knowing XM2 is sufficient. XM2, we just know, we have just seen how to get that, because earlier we have got equation for XM2. In this case, NM2 is weight fraction of B in the mixture. So I just have to locate XM2. There is no need of NM2. So after locating XM2, I'll go to the line R1S, the point where in the intersection occurs, that will be representing mixture M2, and that mixture on this diagram will be represented by the point M2. Okay, so we have got M1 and M2. The x coordinate of point M1 is NM1 and x coordinate of point M2 is NM2. It is not required in our calculations. Then the mixture that is represented by point M2, it will settle into raffinate and extract phases ultimately, and these two phases when they will then reach the equilibrium. Therefore, the conclusion is point M2 not only lies on the line R1S, but it also lies on a tie line which I have shown. The endpoints of these tie lines are R2 and E2, and those 2 points represent raffinate and extract phases that are coming out of stage number 2. So points R2 and E2. So point R2 will represent raffinate phase that is coming out of stage number 2. E2 will represent the extract phase that is coming out of stage number 2. Okay. After this, we have to read the y coordinates. Y coordinate of point E2 will give me y2, and the y coordinate of R2, it will give me x2. So that means in our calculations for stage 2, we have now got the values of x2 and y2, because we are going to use them to find out the quantities of raffinate and extract phases that come out of stage number 2. So equation number 5, it is, we had written it earlier. This is R1 plus S20 is equal to M2, that is equal to E2 plus R2. That is, I can write it like E2 plus R2 is equal to M2. I'll call it as equation number 7. Then equation number 6, which is R1x1 plus S20ys, that is equal to M2 into XM2, that is equal to E2 into Y2 plus R2 into X2. And then now I can write this equation, E2 into Y2 that plus R2 into X2 is equal to M2 into XM2. I'm calling it as equation number 8. In equation number 7 and equation number 8, you have two unknowns, E2 and R2. E2, the quantity of extract that comes out of stage number 1. R2, the quantity of extract that comes out of stage number 2. So you have two equations. There are two unknowns, R2 and U2. You can R2 and E2. You can solve equations 7 and 8 simultaneously and get the value of R2 and E2. So at the end of calculations for stage number 2, you know quantity of raffinate that is coming out of stage number 2, and you know the quantity of extract that is coming out of stage number 1. So calculations for stage number 2 gives us Y2, gives us X2, gives us R2, the quantity of raffinate, and E2, the quantity of extract. So that completes our calculations for stage number 2. Now let us look at stage number 3. So for that, I will show stage number 3. So for stage number 3, the input is the raffinate phase that is coming out of stage number 2, and this raffinate phase is contacted with fresh solvent. So R2 is mass or mass flow rate of the raffinate phase, X2 weight fraction of cyanate, S30 mass or mass flow rate of the fresh solvent that is admitted to stage number 3, Ys is weight fraction of solute in it, then E3 is the extract phase coming out of stage number 3, R3 is the raffinate phase that is coming out of stage number 3. So before we start our calculations for stage number 3, what quantities are known to us? R2 and X2, they are known from the previous calculations. S30, it is known to us. Ys, it is also known to us. So, first, uh, we have to write steady state total material balance. So, it will be written as S2 plus S30, that is, sorry, R2 plus S30. R2 plus S30 is equal to M3, which is the amount of mixture that will be obtained in stage number 3, and that is equal to E3, amount of extract phase, plus R3, the amount of raffinate phase that comes out of stage number 3. Now I am calling it as equation number 9. Then let us write steady state material balance for C. So it will be simply written as R2 into X2 plus S30 into Ys, that is equal to M3 XM3, that is equal to E3Y3 plus R3 X3, and I am calling it as equation number 10. From equation 10, I get M3 into XM3, that is equal to R2 into X2 plus S3 into Ys, that is XM3 is equal to R2 into X2 plus S30, it should be S30. From equation number 10, we get M3 into XM3, that is equal to E3Y3 plus R3X3, or you can express it in terms of known quantities. So it will be M3 into XM3, that is equal to R2 into X2 plus S30 into Ys. So that gives us XM3 as R2 X2 plus S30 into Ys divided by M3. And then from equation 9, you have XM3 is equal to R2 X2 plus S30 into Ys divided by R2 plus S30. So this equation on the right hand side, all quantities are known to us, and you can get the value of XM3. Okay, now let us follow the material balances on the ternary equilibrium diagram. So first we will connect R2 and S2 to indicate that in stage number 3, raffinate from stage 2 is mixed with fresh solvent. So R2 will be connected with S. Then we have to locate point M3. For locating point M3, we need to know NM3 and XM3, but knowing XM3 is sufficient because in this case NM3 is weight fraction of B in the mixture. So let us use XM3 to locate M3. So XM3 is located over here, and then we go on to the line R2S. At the intersection, you'll be having point M3, and this point M3 will be representing the mixture in stage number 3. This mixture, it will settle into raffinate and extract phases, which will come to equilibrium. Therefore, M3 will also lie on a tie line, and endpoints of this tie line, they represent the raffinate and extract phases that are coming out of stage number 3. So these points are R3 and E3. So a tie line and the endpoint, a tie line through M3, and the endpoints of this tie line will represent the raffinate phase and the extract phase that comes out of stage number 3. Point R3 will represent the raffinate phase or that comes out of stage number 3, and E3, it represents the extract phase that comes out of stage number 3. Please note that R3 and E3 on the ternary equilibrium diagram, these are points representing the raffinate and extract phases that come out of stage number 3. Okay, so after locating points R3 and E3, we will read the y coordinates. Y coordinate of point E3 will give us Y3, and the y coordinate of point R3 will give us X3. So knowing Y3 and X3, you can get the quantities of raffinate and extract phases that comes out of stage number 3. So equation 8 is R2 plus S30 is equal to M3, that is equal to E3 plus R3. I can write it like E3 plus R3 is equal to M3. I will call it as equation 10. Equation number 9 is R2x2 plus S3 0 into Ys, that is equal to M3 into XM3, that is equal to E3Y3 plus R3x3, and then I can write it like E3 into Y3 plus R3 into X3, that is equal to M3 into XM3, and I am calling it as equation number 11. In equation 10 and equation 11, there are two unknowns. Which are those two unknowns? You have one unknown is R3, the other unknown is E3. What is R3 in equation 10 and 11? This is quantity of raffinate that is coming out of third stage, and E3 is the quantity of extract that is coming out of stage number 3. So you have two unknowns, you have two equations. You can solve those two equations simultaneously and get the values of R3 and E3, that is quantity of raffinate and extract phases that come out of stage number 3. So in this way our calculations are completed. So since there are only three stages, we have done calculations for each stage. For each stage, we have found out the quantity of raffinate and extract phases that come out of those stages. So in this way, you have to do calculations for multi-stage cross-current liquid extraction. We have understood those calculations with the help of a 3-stage cross-current liquid extraction operation. I hope you have understood the concept. I hope you have understood how to follow the material balances on the Turner equilibrium diagram. In my next lecture, I'll be discussing one numerical that is based on multi-stage cross-current liquid extraction operation. For now, thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it and hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. Also, you hit the like button if you really like my videos, and you please give your feedback in the comment section. I'm sure you have learned something at the end of today's discussion, and I'm sure you'll be with me in my next video where I'll be discussing a numerical that is based on multi-stage cross-current liquid extraction operation. For now, thank you. Have a nice day. Bye bye.